So I think we're good to go. Our first speaker is Charlie Fancher.
You got it, nailed it.
Okay. So now I'm gonna try to pass the test. So Charlie graduated from Worcester Tech.
Yeah.
With a bachelor's degree in physics, and then did his PhD in William and Mary in the physics department, and then joined NRL for a couple of years as a postdoc, and now is working in MITRE on quantum computing. So I believe his original field was physics, which was quantum physics related, or if I don't remember, quantum sensing.
Quantum sensing, yeah, that's right.
And now he's also working in a group doing work with quantum computing, and that's what he's doing. So welcome.
Okay, thank you. Okay, so I'll just read the. Yeah.
Sorry.
No problem. Okay, all right, so let's get started. So it's exciting what we're going to kind of cover in the talk today. So the first thing we're going to do is, I think we've already got a pretty good motivation, so I can spend a little less time on this. Motivate quantum technology in general. Then we'll get into motivating quantum computing specifically. Then there will be kind of like an introduction to quantum computing geared more towards undergraduate students and kind of like a more high-level qualitative type introduction. Then we'll get into what our group specifically is doing in quantum computing, what the group at MITRE is doing. Then we'll kind of wrap up with how and whether to get involved in a quantum career, what kind of motivations might have to do that. Oh, and I should say, if you have any questions, just raise your hand as we go through. Raise your hand, ask the questions, have it answer whatever you want to know. Okay, so first let's motivate kind of broadly quantum technology. So you can kind of break quantum technology into a number of different pieces. In this, I've broken it into three and a half. The first is quantum computing, and so the main kind of headlining application area of quantum computing, at least as of now, is its ability to break asymmetric cryptography, do things like Moore's algorithm to factor prime numbers more quickly. But I'll get to some of the other application areas in the next slide. So that kind of motivates the second area, which is not quantum at all, but something called post-quantum cryptography. So the idea here is to develop different types of classical cryptographic techniques that are resistant to an attack by a future quantum computer. So a future quantum computer could do a number of different things more efficiently than current classical computers, but it can't do everything. It's not a panacea for every kind of application. And there are certainly certain things like finding the smallest vector on a lattice and any number of different things that's not particularly efficient at. And so right now, NIST Petersburg actually is working on picking some finalists for different protocols, different post-quantum cryptography protocols. They say early this year they'll look up some finalists, but who knows what that is. So the third here is quantum communications. So one of the application areas here is provably secure data transfer, or at the very least, provably secure key transfer with something called quantum key distribution. So you can distribute quantum keys between, let's say, two different buildings within the same city. There's also been some demonstrations where you can start at a base station on the ground, send it up to a satellite, and then somewhere else, another base station. Kind of the more speculative applications are things like better networks of sensors, like enhanced clock synchronization, things along those lines. The third kind of quantum piece is quantum sensing. So that's what I spend most of my time in. I spend a portion of my time in each one of these different things. But most of my time is on quantum sensing, which is using quantum states and extracting information from those quantum states about fields, forces, and time. Things like electric fields, magnetic fields, accelerations, rotations, all sorts of interesting things like that, and doing so in a smaller slot package, smaller space-weight power, or doing it with interface. Okay. So now, I'm going to briefly touch on a few of the application areas for quantum computers before getting into a brief introduction to what quantum computers are. So the one that everyone likes to talk about is the ability to break a lot of the current cryptographic schemes, which is very true, and leads to the post-quantum cryptography piece that I talked about. something, there's all sorts of other things that they can do, though, at least that we know of so far. One of them is the ability to more quickly sort through unsorted data. So let's say you had a problem like this. Let's say you had a phone number and you wanted to figure out who that phone number belonged to. You didn't have Google. All you had was a phone book. So the question is, is there an efficient way to look through the phone book and figure out who that phone number belongs to? Going the other way is easy because the phone book's alphabetized, right? So classically, you go through and then you go through pretty much every single person in the phone book, and then you can figure out who it belongs to. With a quantum computer, you can do that in a more efficient manner. Things of that nature in a more efficient manner. Okay, so talk about the cryptography piece. There are also certain parts of machine learning and artificial intelligence pipelines. So there's all sorts of different pieces that go into these things. One of them that is kind of particularly inefficient, or at least could be more efficient with more near-term quantum computers, is random number sampling. And that's something you can do on more noisy quantum computers, kind of more near-term computers. Something that I think is particularly interesting is material and drug discovery. So it kind of makes sense. It's hard to simulate something that's fundamentally quantum with something that's fundamentally classical, a classical supercomputer. And it's a better match if you simulate it on a fundamentally quantum system, either a quantum computer or you can make just a simple quantum simulator that's not necessarily a universal gate computer, but can simulate some of the Hamiltonian, some of the ways that either the drugs interact or the way that some of the materials interact. Kind of the last piece here are optimization problems and logistics problems that can be solved with machines like the D-Wave annealer that are not universal gate computers, but nonetheless could prove to have some interesting applications. Okay, so there's all sorts of different things that you could do with a future quantum computer. Now we'll kind of get into what a quantum computer is and a kind of a brief qualitative introduction to what a quantum computer is and what principles make it fundamentally different and perhaps fundamentally more powerful in the future than a classical computer. Okay, so you kind of see on the right-hand side, there's all sorts of things in the news about different types of quantum computers. But I can tell you right up front, no one has a mature quantum computer, and there's a worldwide race to build one, and there's a giant question mark on when that's going to happen. It could never happen. It could happen in my lifetime. I hope it does. I think that'd be really neat. But there's a big question mark in there. Okay. So the fundamental building block of a quantum computer are qubits, are physical qubits. These qubits are different than classical bits because they exhibit a number of phenomena, three different phenomena that I'll kind of talk about in the next couple of slides. The first is superposition, which is the ability of these qubits to be in more than one state at the same time. The second is entanglement, which is the ability of these systems to be correlated more strongly than what is classically possible. So what that means is you can kind of interact with one, perform some gate operation on one qubit, and it affects another qubit, which is not something that classical computers do. Okay, the last one is interference, which is the ability for different computational paths to kind of cancel out, to have negative state amplitudes, and the ability to kind of come to the more probable route to the correct answer at the end of some algorithm. Okay, so we'll kind of go through each of those three things: superposition, entanglement, and interference, and then we'll get into what MITRE does in quantum. Okay, so with superposition, what it fundamentally does is it changes OR to AND. So with classical bits on the left-hand side here, they can be in either state 0 or state 1. So that's all the classical bits in this computer or any your smartphone or whatever you have. So there's any number of physical implementations of these things. With this, we've chosen to show a capacitor. The uncharged one is a 0, and when it's charged, there are millions of electrons that flow from one to the other, and that represents a digital 1. So you can be one or the other, but that's kind of it. Where a qubit has any number of physical implementations as well, which I'll get to in a couple of slides. But here we've kind of shown a spin 1/2 particle, so think of the spin of an electron. And so the state of this thing can be this blue arrow here. So it could be in some superposition of a 0, which is kind of up at the north pole of this block sphere, and a 1, which is at the south pole of this block sphere. So it can be anywhere on that unit sphere. So it can have any amplitude you want of the 0 state, that's your alpha, and any amplitude you want for 1 state, and that's your beta. Okay, so we change the or to the end. Okay. So what happens when you have superposition plus entanglement? That's the kind of two pieces there. What the superposition buys you is that allows you to simulate many different inputs all at the same time. So with 2 qubits, you can represent state 0 and state 1. Sorry, with 1 qubit, you can represent state 0 and 1. 2 qubits, you can represent 4 things: 0, 0, 0, 1, 1, 0, and 1, 1. Same with 3, and on and on. So what that allows you to do, n qubits, you can have 2 to the n different inputs that you can use to build. So you got to show the capital and sort of your capital. It's important to show that. Okay, so classically, what you have to do is apply an algorithm, whatever algorithm you have, to one input at a time. Where the quantum computers, what you can do is you can kind of load up a whole bunch of different inputs into this state space here, into your superposition of different states. And then through entanglement, if all these things are entangled together, when you apply gate operations, it affects all the things simultaneously. So what it allows for is massive parallelism. So that's one of the kind of the key components. So it's a big state space and massive parallelism, and that allows for that's kind of 2 of the 3 things you need for massive speed up computation. Whatever computation you can do with the system. So here's a copy. The output is randomized. So that's something that I should have kind of stressed in the previous slide. Okay. So when you have a state here and you perform a measurement, let's say you kind of shine a laser on it and you detect a photon out, you do any number of different things. The only thing you're going to get is you're going to get a 0 or you're going to get a 1. You're not going to get your alpha or your beta. You're only going to get one or the other. And it's going to happen with some probability depending on how much weight you have in your 0 and how much weight you have in your 1. Okay. So the output of your whole computation that's stored in that giant state space is only going to be a series of 0s and 1s. And without quantum interference, it's going to be kind of randomized. You have to perform that computation many, many times to figure out what your kind of alpha and your beta values are, to kind of make sense of what your output is, make sense of the answer you're getting. But if you have another piece, the third piece, quantum interference, then we can kind of cancel out some of the unwanted amplitudes. Okay. So kind of qualitatively, the way this would work, let's say you're kind of flipping a coin, you do it classically, and then you do it with quantum mechanics. So classically is on the left-hand side here. So you start with heads, let's have this thing here. And then you flip it, give it a 50-50 chance of hitting heads or tails. You do it again. You're always, no matter how many times you flip a coin, it's going to be 50% heads, 50% tails. And there's not much you can do about that, assuming you have a fair play. But when you do it quantum mechanically, you can start with your block sphere here at the top. You kind of flip it, which is a rotation down to the equator. Then if you were to measure it there, you would have a 50-50 chance of measuring heads, which is up, or tails, which is down. You do that same rotation, the same rotation that got you to the equator. You rotate that kind of state vector the same amount, and you're 100% of the time you get tails. The tails is represented by here's the state 1 here. So these kind of 2 pass and right cancel out, and you're kind of preferentially selecting what you think your right answer is. So those 3 things together give you the kind of the power of okay, so we're all experts on that now, right? Yeah, okay. So I got a couple slides on kind of what some of the physical implementations of these quantum computers are. Then I'll get into the work that we're doing. Okay, so when you choose there's a couple different physical implementations of a quantum computer. And it's difficult to figure out which one is the best. And I'll tell you, I don't know which one is the best. I don't know if anybody does. But what you can do is you can write down a wish list for your qubits, but it's going to be long and it's going to be sometimes contradictory. So what you want is you want them to be well isolated from the environment. So remember what I said is whenever you take a measurement of this thing, it's going to collapse to either 0 or 1. That kind of destroys your whole computational process. And within your algorithm, you're going to need to run 10,000, 100,000, or some huge number of gates and kind of hold this coherence for a very long period of time. So what you want qubits that are well isolated from the environment, from the room, from the table, from whatever kind of things are not part of your system. So you want them decoupled from that. You don't want them to get lost or absorbed. There's all sorts of tricks you can play. You can put these things in vacuum. You can make them cold. You can surround them with different types of fields to isolate them from different things. So that's kind of one thing. The other thing is you want to have good control over your qubits. You want to be able to make them interact with your field. You want to be able to flip them in any which way. So you want to have control when you want it, and you want them to be completely isolated when you don't want to touch them. So those are kind of a little bit contradictory. So you also want the different qubits to talk to each other very efficiently. So that's also kind of at odds with the first one. Is you have a bunch of these different qubits. You want them to kind of be individually connected to each other, but not to anything else. You want to have a good control over that. Okay. So what are the solutions that some people have talked about? So like we kind of talked about earlier, there's this first kind of column with their superconducting qubits. So IBM fits in there, Google, Rigetti, all sorts of different players in this field. So this is the one that typically has the most bits. It plays the most bits. That's the way these things work. It's made up of a bunch of these very little things called Joseph's injunctions. The way these things function is they're similar, the way, like kind of qualitatively, the way you can think about it is kind of current flowing in one direction across this Joseph's injunction and the other direction across the Joseph's. So then you kind of pattern, so you can kind of pattern them out all on one little chip, and they talk to each other with wires. That's kind of how these things work. So we have this giant refrigerator. So this thing is about yay big, about mean tall. So it takes liquid nitrogen, liquid helium, a dilution refrigerator, a whole bunch of electronic controls. But what you get easily machinable qubits. They're pretty fast, and depending on how well you manufacture them, they can have pretty long coherence times, relatively long coherence times, especially in comparison to how fast your gates can be. They can be very fast. That's kind of the advantages here. So this is kind of what I worked on in graduate school. So I worked on neutral atom systems, not for quantum computing, but very similar technology. So you may have heard about IonQ. They're at the University of Maryland. Now they've kind of moved their headquarters down to North Carolina. They still have a presence there. Places like Honeywell out of Minnesota, Botswana in Colorado. There's all sorts of companies that work on it. So the basic idea is your qubits are different electronic states inside either a neutral atom that's held inside a vacuum chamber, or an ion, which is just an atom that you strip an electron away. So they're easier to trap in electric field. So this is an ion chip. I believe that's also a way to manipulate the ions. So one of the disadvantages here is that a lot of your gates are done with lasers, which can be kind of difficult to control, and they can be pretty expensive. So it's also creates some crosstalk between the atoms, but every single atom is the same as every other one. So you don't have to worry about manufacturing imperfections. So that's the big selling point. It's admittedly biased in that way. Okay, so the kind of the third approach, there's more approaches, but we've just kind of picked 3 to show here. The third approach is photonic qubits, where the qubits themselves are photons. They do some interesting process to make the photons interact with each other and perform gates on them that I don't quite understand. But their approach is kind of interesting in that they started with a massively scaled approach. You can have all sorts of different gates, all sorts of different photons, and then they're trying to work back to get the individual gate controller. So this is kind of starting with a few gates and working way up. This is kind of coming at it from the other way. So, okay. So any questions here before we move on to what MITRE does? Okay. So, tell you, MITRE is a company, has about 9,000 people, and about somewhere there's tens of us that work on anything quantum related. So we're a small portion of the company, but we're growing pretty rapidly. So our role is typically to be a neutral arbiter to the government, and it kind of advise the government in any number of different areas. The area that we're in is kind of quantum technology, and in quantum computing, our role is a neutral arbiter for evaluating a lot of the different approaches that I showed in the previous slide. Kind of one, kind of bring some hype back down to reality, because you could just imagine if you're a salesperson for one of these companies and you're talking to someone in the government, you might have some rose-colored glasses to say, oh, you know, my device is the best one, you should give me funding, and I'll promise you X, Y, and Z in, you know, some small number of years. So that's one of our jobs is to kind of be more realistic with projections for the performance of these things. The second is to benchmark, find a way to benchmark the performance of qualitatively different architectures. Got to find if you can have one number or maybe two numbers to compare some of these different things. Third is forecasting the usefulness of these quantum computers against some different number of applications. Figuring out when that might happen, which is admittedly a very difficult job. And kind of like as an aside, one of the things that we do is quantum workforce development. We work with a number of different organizations to try and grow the domestic workforce in computing, quantum computing, sensing, and networking. I'll kind of get to that at the end, but just tell you that there's a lot of money in this field. So this is you know, definitely at least a good career choice. It's my personal opinion, not my. Okay. So one of the things that we do is we try and create realistic metrics for how well these different quantum computers perform. Not only how well they perform, but how well, kind of how to compare them to each other. So we can start on the left here, which is kind of a push factor, which is kind of measuring how well, let's say, you know, one of the latest IBM release. They say, well, we have this many qubits and it has this kind of an error rate. Then, you know, kind of what can you do? How useful is that? So one of the ways that you can describe that is you can take a plot that looks like this. On the y-axis here is the number of qubits, and on the x-axis is the number of gate operations you can do on those qubits. So this kind of metric here is called the quantum volume. So the quantum volume is kind of formally described as you take the minimum of those two things. Your number of qubits or the number of gates that you can have random 2 qubit gates you can perform with this. So that's kind of where we are now. And then on the other side is what do algorithms need to provide a useful function? So they need, for example, some number of qubits in the 10, you know, 100, couple hundred range, but they need 10,000, 100,000 gate depth to do that. So you can say, well, this number is a couple hundred. This number is 10,000. So is this metric useful? Which is a kind of a square here, but we need to make it a little more rectangular. So this is trying to make it a little more rectangular to make it to make this benchmark a little more towards what's actually practical. To say, well, can we make it, you know, here's the number of the qubits, and then this is the number of qubits squared or cubed or whatever you need for any particular element. That's kind of a project that's currently ongoing to get a better benchmark for how these different things perform. So it turns out you're often limited by what your gate error rate is instead of the number of qubits. Okay. So a question that we get asked a lot and never have an answer to is, when are we going to have a quantum computer? And I tell you, I don't know. And I would hesitate to believe anyone that told you with any kind of certainty. I hope it's within my lifetime, but I don't really know. Okay, so what we can do is we can take that benchmark that I talked about earlier, which is the quantum value, plot that here, and then plot the year here. So these are all publicly released quantum volume information from a number of different companies, with IBM, Honeywell, and IIT. And so what we can say is, well, this is where we've been. Where this is going to go in the future, we don't really know. But we can say, well, it kind of looks like it's doubling every year. So what happens if you draw this line and we say this quantum volume is doubling every year? We say, well, hey, we get to something sort of interesting about 2040, 2050. So let's at least an exercise you can do exactly what the slide is going to look like in the future. Not exactly. Yeah.
So that line that says one last because you hit.
Yeah. So what's kind of interesting about that is, so that kind of gets into something else called error correction. So there's any number of companies that have a bunch of different qubits, but the thing is they all have some error rate associated with preparing it in a certain state, doing gate operations, and then reading it out. So one of the things that you can do is if you have enough bits and you have a low enough error rate, you can kind of smush a number of different qubits together to make one sort of perfect qubit. That's often called a logical qubit. So that's kind of the building block of some of these algorithms, a logical qubit. Or I guess an error corrected qubit is another way to say it. This trend, I believe this trend line is every year. That might not be true. At least that's what I think that's what Brandon told me. So he made this line. I think that might be doubling every year. At least that's what IBM claims they'll be able to do. Honeywell claims 10 times every year, so they think they're gonna go a little bit faster. So yeah.
1 million by 2030, that's 1 million.
So this is one, okay, so that's a good question. So what's shown here are really big numbers that don't actually correspond to what's up here. IBM made this metric called quantum value, and they wanted to have a quantum Moore's law, just like the Moore's law that you put up. And so they said, well, our number is going to be 2 to that, whatever is the minimum between the number of bits and the number of gates. So that if you add 1 qubit and 1 gate, it kind of doubles, right? It's all marketing. But so this is the kind of 2 to that number. And then what we've done on this plot is to pick a log to this number and then stick it up here. Yeah.
So I guess in a sense, it's not technically like Moore's law, just Moore's law actually. This is not like.
No. I think this is more along the lines of what, if you put this to a line and just kind of project it into the future, what's going to happen. So I can tell you it did kind of become a self-fulfilling prophecy because you just had more and more money dumped into it. What I mean is they had the money to do the research to drive the change in the technology. It's sort of in that way. So maybe I just talk about this for a second. There's a whole bunch of money, venture capital money being dumped into these companies now. And what may happen in the future, who knows, is if these companies don't start producing revenue, they may start pulling back that money. And there may be a quantum there. So they might not have that. I think it's called the virtuous cycle of people buy more and more of these integrated circuits, and then they dump more and more money into the R&D of the circuits to make them better, and then just kind of snowballs like that. But if we don't hit that kind of positive feedback loop, you can make it something like that. Any other questions here? Okay. I think we'll get into the why should I care portion of the talk, which is if you want to get into a quantum career, why would you want to do it, and then how do you do it? The honest answer, at least a good motivating factor, is money. There's a lot of money flowing into this kind of quantum computing space. First of all, quantum computing, then sensing and networking. And a common sentiment I've heard is our hiring speed is limited by the number of qualified applicants, not by our funding. That's kind of like a good place to be, right? It's like if you're a qualified applicant, you're gonna get hired somewhere, and they're gonna pay you a decent amount of money. So this, I was actually in touch with people at Quantum Futures. They're kind of like a recruiting firm. They told me I could put up this plot. As you can see, this is kind of after 2 years in the postdoc. This is kind of how much you're going to start to make, and then 1 to 2 years, 3, 5 years plus in any number of different subfields here. Yeah, this didn't come out very well. Okay, so you can see here so this is you go to graduate school, you do a 2-year postdoc, so that's a long time investment. So you can make anywhere from 100 to 100. I guess this is 145 for an algorithm specialist per year, and then it just kind of marches up, and then 5 years plus 200 to 250. Right? Whether you actually make that much, I have no idea. I'll tell you when I get there. But I guess, yeah, the point of this is there's been billions invested in these quantum computing companies, and they're really looking to hire people. So I guess this is the second to last slide. There's possible ways to do this. So I can tell you this is the way I did it. Not necessarily the best way to do it, and not necessarily the way that I would do it if I had to do it all over again. The easiest way, the fastest way, at least the fastest way to get employed, start with a bachelor's degree, find someone to hire you. That's likely going to give you your highest lifetime earnings. If you just plot out and integrate your salary over a number of years, that's probably going to give you the most amount of dollars. But this is kind of a less clear path to kind of getting into one of these quantum computing companies, but that's kind of changing. I suspect that'll change in the next couple of years. There's kind of a big push to kind of better match the curriculum to what these companies need. The next way you can do it is to get a master's degree or some sort of industry experience. If you're going to get a master's degree, a good way to do it is to get your employer to pay for it, so you don't have to pay tuition, and then hopefully they'll pay you your salary to go as well. And of course, moving jobs gets easier once you get your first job. And then it's so if you really want to go to graduate school, it's going to be a long time. It's going to be a lot of work, and they're not going to pay you very well. But one of the things that I looked at when I was deciding many years ago to go to grad school is that they historically low unemployment rate, even during big recessions. It's sub 3%, even including the 2008 recession. To get more autonomy, but it takes quite a long time to get there. So I'll just kind of do my conclusions here, and then we can talk about whatever we'd like. So quantum computing can have all sorts of different applications, including the big one being breaking asymmetric. Some current asymmetric cryptography protocols, qubits are qualitatively different. I just walked through here, they can be anywhere in the middle. We're kind of a neutral arbiter for all these different quantum computing approaches, and quantum computers can be rewarding. I'll wrap it up and thank you for your attention.
So before you mentioned that you guys were thinking about ways to
Yeah.
when you said that, were you saying
I think random number generator. Yeah. Well, that is an application.
So is it like are you guys able to prove that it's like truly random?
That's an interesting question. I'm not up on I'm not up on how exactly you would prove it. But as I understand it, yes. As far as you believe it, right? Yeah.
Is the underlying nature, it's range
So it's like, you said, like, it would be like a uniform distribution.
Those are the distribution that you're getting. This does this right. I'm guessing it's probably more like random uniforms. No. Have to talk to this.
Yeah. So the way I don't know I've heard of these companies and I read their websites. I don't know the physical mechanisms that they use, but think of the coin flip this way, right? If you had your vector on this block here, like you can put it, if you know you can put it there every single time, and then you measure it and you measure it and you measure it, then you can be guaranteed you get a random 0 and then a 1, 0, 1, 0, you know, whatever random pattern. Because you know that you have a 50-50 chance of being here, 50-50 chance of being there, so long as you believe quantum mechanics works the way you think it does. Which, at least, no one's come up with an alternate path. Yeah, so this one? Yes. So is the question, is it on this slide? Is that the question?
Yeah, so you have a situation here, something like that. So it's all different ways, different methods to the algorithm to do what is the
Oh, the different hardware slide.
Yeah, yeah.
Oh, sure. Okay, I'll flip to that slide. Is it this slide?
Yeah.
So the question is,
They're all like different ways to do, so we can get it like a 0, 1, also.
exactly. So at least what question is, these are all different ways to represent zeros and ones. And then it is the question, like, how do you physically do that? Like, what's the physical thing behind each of these? Yeah, so that's, okay, great question, okay. So I can kind of I'll just go from left to right, describe the different physical units here. So with superconducting qubits, the physical qubit is this tiny loop here called the Josephson junction. So there's a little bit of, so it's mainly superconducting with a little bit of non-superconducting here. And they have different quantum states, different flux states. So those are your 0 and your 1. One of them is kind of, rotates to have your flux up, and the other rotates to have it down. So it's not technically true, but the way I think about it is you have a circuit, you have current flowing one way, and you have current flowing the other way. So that's one of them is 1, one of them is 0. That's a physical mechanism. The physical mechanism for the trapped atoms and ions, that's a little bit different. So within each of these, so you can actually see the individual ions here. So they're kind of glowing. So we'll take the ions for an example. So each of these ions has a number of different electronic states that it can be in. So typically it has a ground state. It has any number of excited states. You can put it in those states with lasers. You can put it in different states with applied magnetic fields, applied electric fields, and then so you kind of pick 2 of those states. You say one of those states is going to be my 0, and one of those states is going to be my 1. And so each ion is 1 qubit. And then the way you get between the 0 and the 1 is either with a laser pulse or with something like a microwave pulse. Okay, so now the photonic ones, this is a little more complicated. This is something I understand the least. But the basic way that I understand photonic qubits, think of it with polarization. So you have one photon, a single amount of light, one photon. And it can either be vertically polarized, so the electric field bounces up and down like this, or horizontally polarized like this. And so this is a 0, and this is a 1. I'm sure there's a lot I know there's a lot I don't understand about this, but that's really kind of qualitative how I think about it. Yeah, keep up, please.
Yeah, I see
Yeah. Oh, no, I'm going the wrong way. That's why it's not working. This one.
Yeah.
So the question is,
Yeah.
you know, these numbers are really small, right?
Yeah.
And then what's going on with this? So these numbers, what these represent is actually on this previous slide, how big of a circuit you can make, which is what's the minimum number between the number of qubits that you have, which is 50 or 100 or something like that, between that and the number of gates you can apply before you get to a large enough error. And typically you're limited by the number of gates that you have. So that's why they're pretty small. This is, typically 10, 50, maybe 100, some of them. Yeah, around 100. Yeah, please.
Can you flip back to the three?
This one? Yeah.
So I have two questions. So the first one is, why are all these big companies or IBM Google so focused on the same thing? And the
Okay.
second one is, how well do these approaches the lithography can be applied and scaled out?
Okay, so I'll repeat the question for people on Zoom. So the first question is, why are places like IBM, Google really interested in superconducting specifically? Yeah. That. And the second question is, can you use E-beam lithography to make the Josephson junctions smaller and smaller, kind of shrink them down? So the answer to your first question is Josephson junctions have been around for quite some time, as have trapped ions and atoms, but they're easier to communicate with because you communicate with them via microwave. And microwaves are like a very well-established technology. There's a lot of off-the-shelf components. They're all solid state. You don't have to worry about lasers. And so what you need are people that can make chips well and electrical engineers. And I'm kind of glossing over a lot of stuff. But you don't need people with optics experience. You don't need a ton of physicists. And so frankly, this is a good choice to start with. And I understand why they did it. And I don't know which is best between these two. And then to your second question, can you use E-beam lithography to make them smaller and smaller? Probably. I don't know enough about E-beam lithography to give you a better answer than that. I know there's all sorts of techniques to manufacture these things, and beyond that, I'm not sure. Good. Okay. Excellent. I think we're almost ready for the.
It's essentially a time. It's a long way from there. Also, we're trying to find they really move light around from the structures of the scale. So it's usually a scale effect, but a lot of the stuff
It's good. I learned something new today. So it's
good
good.
for the success.
Yeah.
Here for us people.
I think we're gonna start at 2:05 the next talk, so a few minutes